Hello, everyone. It is with pleasure I introduce Dr. Lawrence Krauss. Dr. Krauss is the Foundation Professor of the School of Earth and Space Exploration at Arizona State University. He has made significant contributions in cosmology, where he was one of the first physicists to suggest the existence of dark energy, a substance which may be responsible for 68.3% of all the total energy in the observable universe. Dr. Krauss is also a tireless advocate for public understanding of science. He served on the Science Policy Committee for Barack Obama's 2008 presidential campaign, contributed articles to The Atlantic, The New Yorker, and Newsweek, and written several New York Times best-selling books on science, including his previous book, the well-noted and well-regarded Universe from Nothing. My first exposure to Dr. Krauss's work came with one of his early books, The Physics of Star Trek, which I found enthralling for its thorough and altogether serious look at the physics, plausible and otherwise, of one of my favorite series. As a brief aside, Dr. Krauss, I feel like there was a missed opportunity. You wrote a follow-up called Beyond Star Trek, and I feel it should have been named The Physics of Star Trek 2, The Wrath of Krauss.
You're taking that out of my I put that in my appendix.
Oh, you did?
Yeah, exactly.
Oh, you did now.
Okay.
Today, Dr. Krauss is here to talk about his latest book, documenting our current understanding of nature, the history of one of humanity's greatest scientific achievements, the Standard Model of particle physics, and its implications for our existence, and what promises to be the greatest story ever told so far. Join me in giving a warm welcome to Dr. Krauss.
Thank you. Thank you. Thanks. Well, it's a pleasure to be here and see all of you. And I understand it's lunchtime, so I shouldn't go overtime. So I'll make a shorter version than normal because I know you have really important work to do. So, in any case, the quote that I had here along with the music comes from a book that actually a friend of mine who's a filmmaker named Werner Herzog recommended to me, and he, you might have seen his most recent, well, not most recent movie, but second most recent movie, Lo and Behold, which is about the internet, which is nice. So there's another one that just came out, which is a fiction called Salt and Fire that I'm also in as a villain, but it's a weirder movie. But anyway, this book, which is called The Peregrine, is about a peregrine, and but it is a wonderful naturalist book if you ever want to read it. But the quote is what's particularly important, which is the hardest thing of all to see is what is really there, and that's really the thrust of the content of my book, which is that the world we live in is an illusion, and it's been an amazing story for particle physics and oh, look at that. Okay, is there a reason that went off? Auto power off engaged. Auto power off was engaged. So, waiting for projectors to start. Good. I'm very impressed with the technology. So, anyway, the Standard Model of particle physics, and in fact particle physics in general, has been about trying to understand the fundamental structure of matter and energy. And it is really an amazing story of how different the universe is at fundamental scales than the scale we see. And one of the real implications, and one of the reasons the subtitle of the book is called Why Are We Here, is that the universe that we exist in is an accident in a well-defined way, which I'll talk about until the projector gets to there. Let me just get to the slide I want to do, so when the projector actually turns on, which is certainly not now. Light just came on. That's good. We can get to the image I want to show, which is of a window in the wintertime with ice crystals on it. I was actually just in Phoenix where I teach, and I gave a lecture on this, and I had to explain to people those were ice crystals. But here we go. And so these are beautiful. But what I want you to do is think for a second of what it would be like if you lived on one of them. So I say this one, okay? If you evolved on, and we can still use that word in the U.S. If you evolved on that crystal, what would happen? Well, the physicists, I don't know where it is in that one, but anyway, let's say with this one. Oh, no, there it is. The physicists working in this world would say, well, okay, I can work out the forces. The forces along the spine of the crystal are very different than the forces perpendicular. So they'd come up with laws of physics which would explain and predict how things moved, and there'd be one set of forces in this direction and forces in the other direction, and that would seem natural. There'd be theologians who'd say, well, explain why God ordained that direction to be the proper direction for life. And there'd be wars fought over whether that was the right direction or that was the right direction to pray to. And all of that would have significance, which of course is completely illusory. That it is just an accident, and the crystal can point in any given direction. And but it wouldn't seem that way if you lived on that crystal. And that's essentially the world we live in. All of the facets of the world that make it look like the universe is designed for our existence are pure accidents in a fundamental way, which I'll try and describe. And we, of course, the world looks like it's designed for us, but at a fundamental level, it's actually antithetical to our existence, as I'll describe to you. Now, the story's long and winding, and obviously I said I want to give an abridged version so you can get back to work. But so I'll start fairly late into this. But the story actually begins 2,000 years ago with Plato and then works through Maxwell and Einstein, talking about the major revolutions that have changed our perspective of our place in the universe. And one of the things that describes pretty well the progress of science, certainly in physics in any case, is when we know made progress when two things that seem very different on the surface are seen to be different reflections of the same thing. And then we know we've made progress. And that pretty well characterizes almost all the progress in physics over the ages. From, for example, in recent times, the recognition that electricity and magnetism, which seem so different, are really exactly the same thing. And one person's electricity is another person's magnetism. That led to the realization that space and time, which seem different, are really the same thing. And what one person sees as space, another person will measure as time. We live in a four-dimensional universe, not a three-dimensional universe. And those kind of developments have progressively told us that the universe that we see is kind of myopic, because we perceive these three-dimensional slices of a four-dimensional universe, which is why it seems so non-intuitive to us that the universe is four-dimensional. And when I'm running with respect to you, I'm seeing a different three-dimensional slice of a four-dimensional universe, which is why things seem strange and relativity does what it does. And I talk about those things at great length in the book. So though up to that point we developed a theory of electromagnetism and a theory of gravity, and all seemed well until we got to a later stage. And I want to begin the later stage with this guy who all of you know, I assume. It's Richard Feynman. And who was probably, was one of the greatest physicists of the second half of the 20th century. And what he won the Nobel Prize for with others was the recognition that, of course, at the fundamental level, the world is quantum mechanical. And if we want to have a theory of electromagnetism, we need to put it in accord with quantum mechanics. And the theory they developed, called quantum electrodynamics, is a theory that merges electromagnetism and quantum mechanics. And he presented a way of thinking about this to understand the electric force between two charges, which had been understood by Faraday and Maxwell, in a slightly different way, a way we talk of by Feynman diagrams, as we call them. But it's particularly interesting. So this is an electron, and it repels another electron. And it does so by the exchange of a particle, a photon, the quantum of the electromagnetic field. The electromagnetic waves come in particles, and photons are the individual quanta. Now, what Feynman used in developing this is a key aspect of quantum mechanics, which is central to quantum mechanics, which is really the same thing that's used in Washington and corporate America, which are now the same thing. If you can't see it, anything goes. Okay? That's basically it. And we'll learn more about that with investigations over the next year, I certainly hope. But so the idea is that this electron emits this particle, this photon of light, but that's impossible. It's not allowed. The electron just sitting there cannot emit a particle of light, because where did the energy come from? If the photon carries energy, where did the energy come from? The electron is still there. If it's an isolated electron, it can't emit a photon because that doesn't conserve energy. But that's okay. That's allowed by the Heisenberg uncertainty principle, which is responsible for that Washington rule I gave you. The Heisenberg uncertainty principle says if I measure a system for a short time, then I can't know its energy exactly. There's some uncertainty in the energy. So if I emit this photon and it violates energy conservation, that's allowed in quantum mechanics, as long as the photon disappears in such a short time that I can't measure it. It's just exactly like embezzlement. Okay? I'm sure Google does this every day at some level. Because if you get the money, and as long as you put it back before anyone notices, you can do whatever you want with it, right? And that's, there's a lot of trading that goes in that regard. So it's exactly the same. So the photon can violate energy conservation here. As long as it disappears before you can measure it, you're fine. And so the photon is exchanged and it produces that repulsion. Now the key point is the photon has zero mass. It's massless. And that's essential to make electromagnetism a long-range force. So an electron here repels an electron in Alpha Centauri, okay? Or anywhere in another galaxy. And the reason is, because the photon is massless, it can carry an arbitrarily small amount of energy. And if it can carry an arbitrarily small amount of energy, then it can exist for an arbitrarily long time before it has to disappear without violating the Heisenberg uncertainty principle. And if it can exist for an arbitrarily long time, it can travel from here to Alpha Centauri before it's absorbed. So the fact that electromagnetism is a long-range force is uniquely related to the fact that the photon is massless in this picture. Okay? And this photon, because you can't see it, is called a virtual photon because it doesn't really exist. You can't ever measure it. If you look for it, it's not there. Okay? And great. And so this is a complete picture of the quantum theory of electromagnetism. You absorb and emit these virtual photons that can do anything they want as long as you can't see them. And this theory is the best theory in science. It's the best theory in any area of science. So based on this theory, you can make predictions and compare them with observations to 14 decimal places, which you can't do in any other area of science, where fundamental predictions compare to observations. So this is as good as it gets in science. And in the 1940s, when this was developed, this was great. We now have a complete theory called quantum electrodynamics, which explains and predicts perfectly every measurement you can make in atoms and other things where electric fields are relevant. So that's great, okay? And that looked great for nature, but then nature intervened, okay? Nature intervened by the fact that the neutron is radioactive. Now this should disturb you, okay? Because I remember I first learned about it when I was in high school from a guy named Tommy Gold, who was a wonderful astronomer. But it should disturb you because most of the particles in your body are neutrons, right? Neutrons and protons make up atomic nuclei, and for heavy nuclei, certainly there average more neutrons than there are protons. So the number one dominant particle in your body is a neutron, okay? If I take a neutron here and hold it up, it will decay in 10 minutes, okay? And you will notice, maybe to your chagrin, that you've been here for more than 10 minutes and they're still here. You may be praying for your neutrons to decay, but they're not. And why is that? An accident of our existence. So what's neutron decay? Well, neutron decays into three particles: a proton, this is just a fancy way of writing an electron, a proton, electron, and a neutrino, another particle. The key point, however, is that the neutron and proton weigh almost exactly the same amount. The difference between these two masses is 1 part in 1,000. And so the neutron has barely enough energy to decay. If its mass was less than the sum of these three masses, it couldn't decay. Again, it would violate energy conservation. So it's just barely more than the mass of these three particles, which is why it lasts so long, because 10 minutes is a hell of a long time in particle physics units. Okay? I mean, so it seems like an eternity. So this is a very long-lived particle, but short-lived by our standards. So how come you're still here? Which you may be asking yourself. So it's an accident, okay? What happens when I put a neutron in a nucleus? Well, it falls in the nucleus and it gets bound. What does it mean to be bound? Well, some of you know. But otherwise, it means that it takes energy to get out. You lose energy when you get bound. And so the neutron falls in the nucleus, loses energy, but E equals mc squared. So the neutron gets lighter. And when the neutron gets in a nucleus, it no longer has its mass is too small to decay into these particles. So the neutrons are only stable in nuclei by that accident of the fact that the neutron-proton mass difference is so small that when it falls into a nucleus, it no longer has enough energy to decay. And that's why you're here. That's why there are heavy elements. If it weren't for that, carbon, nitrogen, oxygen, iron, all the things that on which our lives are based would not exist. Just because of that fortuitous fact that these particles have almost the same mass. Okay, that's interesting. But more interesting for physicists was, well, this was a little disconcerting because suddenly this implied there was a new force in nature. The neutron was discovered in 1932, okay? Suddenly a new force had to, because electromagnetism can't cause this decay, and gravity can't cause this decay, so there had to be some new force in nature that would cause that decay. And of course the question is, what kind of force is it, and how can we understand it? The first person to write down a theory for that, any kind of theory, was one of my favorite physicists from the 20th century, Enrico Fermi, who was the last particle/nuclear physicist who was equally good at theory and experiment. The two fields have become sufficiently complicated that you can't do both now. Okay? He was the last one who was able to do both really well. He also, historically, in the Manhattan Project, was the one who was assigned the task of building the first nuclear reactor, the first sustained chain reaction. And so they built it in the University of Chicago underneath the football field, which I've always viewed as an inspired choice, because if anything went wrong, you just kill football players, there's no loss. So Fermi built that successfully, but he also wrote down this first model of this, and he submitted it to the journal Nature, and it got rejected, which heartens many of us who submit to Nature and get rejected. But he didn't take it well, and he, in fact, said, I'm not going to do theory now, I'm going to just go do experiments, which was good for him, it turned out, because the next experiment he did won him the Nobel Prize in physics. So it worked for him. But as his theory was built upon by others. Now, the really important thing, there are many important aspects of science that I want to try and emphasize, and I try and emphasize in the book because they have relevance well beyond the esoteric physics I'm talking about. Relevance, as I'll describe in some sense, to the quagmire we find ourselves living in right now. But the one thing that's really important about science is that it's like Hollywood. And maybe like Google, actually, probably in that regard. If it works, copy it. Okay? And keep copying it until it doesn't work anymore. It's like Halloween 56 or whatever. As long as you can sell tickets, keep copying it. And so if we have a theory that works, copy it. So here's the best theory in nature. So the idea was, if you have a new force, let's make it look like this force. So we can draw a picture, a Feynman diagram that looks the same, sort of. A neutron decays to a proton. It's made of quarks, but that's a little added complication, doesn't really matter. And then an electron and a neutrino come out. And if this works by the exchange of a particle, then why not imagine this force works by the exchange of a particle? But this force is very different than this force. This force works across the universe. This force, the weak force, operates only on the scale of nuclei. That's why we don't see it on human scales. It only works on the scale of nuclei. So it's very short range, this is very long range. So weak, this is strong. How can you relate those two things? Well, if you make this particle massive, then what happens? If this is very, very massive, then emitting it always produces a lot of energy, because E equals mc squared. So if it's massive, you can't help but have a lot of energy produced here, and that means you violate energy conservation by a huge amount, which means the particle has to disappear very quickly by the Heisenberg uncertainty principle, because otherwise that huge amount of energy would be noticed. So if you emit a particle that's very, very massive, it can travel only a very short time, and therefore only a very short distance before it has to disappear, unlike the massless case. So you want a short-range force, just exchange a massive particle. A long-range force, a massless particle. Everything works fine. But it doesn't. Because this theory gives the best predictions in nature. This theory gives nonsense. Because when you do the mathematics, you get infinities. Physicists don't like infinities. Computer scientists don't like infinities. Mathematicians love infinities. But we don't. So the idea is how to get around them. And this was a fascinating and severe problem. It's so severe that actually in the 1960s, when it was kind of first recognized, many physicists were willing to give up the pretty picture. They said maybe this unification of relativity and quantum mechanics just doesn't work on the scale of nuclei. And it was kind of amazing how easily they were willing to give up this picture. And one of the things about the book is, which is one of the reasons it's the greatest story, it wasn't easy. In particular, there are lots of red herrings and dead ends. And physicists are people. And that means they're pig-headed and prejudiced and biased. And they often want to go in a direction even when that direction is futile. Okay? But the great thing about science is it drags the physicists or the scientists kicking and screaming in the right direction. So the individual scientists may be prejudiced, but eventually, because of nature, they're forced in the right direction. And in this case, these people, and especially, actually, it was interesting, in Berkeley was the main place, but people wanted to give this up, and they created a kind of Zen version of physics, which is appropriate for Berkeley in the 60s. And it was the sound of one particle clapping, basically. But it was the basis of string theory got generated there as a way, an alternative to this picture, and it failed miserably there too. But that's a different book. The point is that these people were looking at the problem, and you want to shake them, because in fact they had the answer. The answer was right there for people if they hadn't been looking in the wrong direction. With hindsight, it's so much easier to see things, to see that the answer was right there, and the answer came from a very different area of physics, superconductivity. So in 1911, Kamerlingh Onnes discovered, a Dutch physicist, discovered that if he cooled mercury down to 4 degrees above absolute zero, then the resistance went to zero. It didn't just become small, it went to zero. And that means if I have a mercury wire and I hook it up to a battery and I start a current going and then I cool it to 4 degrees, I take away the battery, then the current continues to flow. And it doesn't just flow for an hour or a day, it flows forever. It never ever stops because resistance is precisely zero. It seems like it shouldn't be possible, but it is. It's a remarkable phenomenon that he named superconductivity, and it's so weird that it took maybe 50 years to be able to have a theory of this, and it has to do with the rather complicated interactions of electrons in materials, which is nice. Okay, so what's this got to do with what I just discussed? Well, nowadays we have high temperature superconductors, so we can do neat experiments in high school physics classes, because we can put a superconductor now in dry ice, and there's some materials that become superconducting at those temperatures, and then we can play with them in high school classes. And for example, if you have a superconductor in dry ice and you put a magnet above it, the magnet will levitate. Why? Because it turns out magnetic fields cannot pierce the superconductor. They die off the surface of the superconductor. So do electric fields. But that means the magnetic field lines basically get repelled by the superconductor, and that's enough to levitate the magnet. It's a fun little game to play in class. Okay. Again, what's this got to do with anything? Well, now I want you to imagine that you live in this superconductor. And now I ask you, what are the laws of physics in that superconductor? Well, for you, if you live in that superconductor, electromagnetism is a short-range force, because electric fields and magnetic fields, when they enter the superconductor, die off exponentially fast, it turns out. So if you have a quantum theory, if you develop quantum mechanics in that superconductor, you'll describe electromagnetism as a short-range force, and that will mean that the particle that's exchanged is massive. And indeed, in a superconductor, photons are massive. They have mass. They're massless out here. They travel at the speed of light. In a superconductor, they're massive. They travel much slower. It's just the way it is. Now, again, this should start bells ringing in your head, but it didn't for the physicists at the time until finally someone began to think about, well, what if we live in a cosmic superconductor? And what if it's like swimming in water, okay? You swim in water, you feel you're really fast, and maybe Google has a pool here, probably does, I don't know. But what if you fill it up with molasses? Oops, sorry. What if you fill it up with molasses instead of water? Well, then you won't want to go swimming, first of all. But if you did go swimming, you'd swim a lot slower. It'd be a lot harder. You'd feel a lot more massive. So what if we live in a cosmic superconductor, and everywhere through space, I can't resist this, everywhere through space, there's an invisible field permeating all of space, and some particles interact with that field and get resistance and appear as if they're massive, and other particles don't. What if that were the case? Well, then you could draw these pictures, these Feynman diagrams. This is the one I showed you before, but turned sideways. And these are the ones for the weak force, the one that produces that electron neutrino. It turns out there are 3 particles involved, but that doesn't matter. But now, what if these particles are massless, just like the photon? But they interact with this invisible background field that's everywhere, and they act like they're massive in our superconducting world. And that means that the force they mediate looks like it's short range. Well, that would explain how it could be short range, but the neat thing is if they're massless, then the mathematics of the calculations involved by the exchange of these massless particles is the same as that for a photon, and in fact, instead of producing infinities, it produces correct results. Moreover, in fact, the mathematics is identical. So not only do these forces appear similar, in fact, they could be the same force. And nowadays, the picture is that these two forces, which are so different in the world in which we live, each of which is responsible for our existence, the electromagnetic interaction is responsible for all the interactions in the biology of your body. The weak force is actually responsible for the processes that power the sun, as well as the existence of heavy nuclei. And both of them are essential for our existence, but although they're very different, they're really the same at a fundamental level. And at a fundamental level, they wouldn't look at all like the forces we see in the world in which we live. We were dragged to this picture unwillingly, as I say, and for a long time a lot of people went in other directions. And it's amazing to think that we were willing to picture a universe that is so distinct from the universe in which we live, so uninhabitable, if you wish, so foreign and so alien. It's one of the one of the great aspects of science and art and music and literature, is that it forces us to view our own perspective of our place in the cosmos differently, in a way that may not be the way we wanted. So it's an amazing intellectual triumph to propose that, and it apparently works. But at this point, it's kind of religious, right? Just think what I just said. Imagine there's an invisible background field everywhere throughout nature that determines why you exist, okay? It sounds a lot like things you would have heard in the Bible or Star Wars or something like that. So, and it would be just an extraordinary claim without evidence, which is religion. And it isn't, though, because it's physics. And what does that mean? That means if it's there, we have to find it. So if this invisible background field, if this weird, ridiculous picture is true, and it is a ridiculous picture, it's one we should be highly skeptical of. If it's true, we better find it. How do you find it? Cosmic sadomasochism. You spank the vacuum. You spank it hard. What do I mean? Well, all fields in quantum physics, all fields are related to particles. So if I dump enough energy at a single point in space, and let's call this field the Higgs field. If I dump enough energy at a single point in space, maybe I'll kick out real particles associated with that Higgs field. I'll call them Higgs particles. How can you do that? Well, you build the most complicated machine humans have ever built. In this case, the Large Hadron Collider in Geneva, Switzerland, which is a particle accelerator. It's located in Geneva, and in fact, if you go to the airport, and Google probably has an offices there, if you go there, and you'll see the lake and then the little water spout there. But underneath the farmland, right outside the airport, which is beautiful pastoral farmland, 100 meters below the surface is a tunnel that's 26 kilometers around. And what we do is we accelerate protons at 99.9999998% the speed of light in one direction, and then protons at 99.9999998% the speed of light in the other direction. And we try and collide them at certain points, 3 different points in this circle. They go around thousands of times every second. Here's the French-Swiss border, by the way, so they cross the border without passports and all that. Thousands of times each second, which Trump will want to change, no doubt. And this machine was built to be able to see if we could kick particles out of empty space and produce these Higgs particles, if this ridiculous picture actually worked. Now, in this country, we have an anachronistic day we celebrate called July 4th, which doesn't mean anything to anyone else. But now it has a cosmic significance, because on July 4th, 2012, we reported 50 events produced in the Large Hadron Collider that looked like Higgses, that walked like Higgses, that quacked like Higgses, and we thought were Higgses, okay? And in the intervening 5 years, now almost 5 years, all of the experiments have fine-tuned those results, and they have exactly the properties that were predicted of the Higgs particle. Okay? Exactly. This is an amazing triumph, because it means that this ridiculous picture which we are pushed to is real. It means we really live inside of a cosmic superconductor. And it means that we were driven not just to propose that picture, but to build this remarkably complex machine to do it. And to me, this is humanity at its best. The willingness to go where nature takes us, first of all, independent of whether we want to go. But then to amass the resources to build this machine just to determine why we're here. And of course, one of the benefits of science, which many people herald and is responsible for all your jobs, is technology. which is great. But it's a little bit unfortunate too, because that means when you have science, and people always say to me, well, what good is it? What is it? Does it make a better toaster? Does it make a faster computer? What is it? And if it doesn't do those things, it looks like it has no utility. But of course, we don't ask those things about a Mozart concerto or a Picasso painting or a Shakespeare play, or you pick your favorite whatever, an Eric Clapton song, whatever. And science is exactly the same. The real virtue of science is exactly what I said earlier. Not the technology it produces, which is nice, but its cultural significance, which is the fact that it forces us to get out of our myopic picture of ourselves, just like art, music, and literature, to see ourselves in a broader sense, to get a better perspective of our place in the cosmos. In this case, to be willing to build these amazing machines. I call the Large Hadron Collider the Gothic cathedral of the 21st century. The Gothic cathedrals were beautiful things built over centuries by thousands of artisans using the highest technology at the time. They didn't know how to make these ceilings so they wouldn't fall in for a long time. All working together. Well, the Large Hadron Collider was built by 10,000 PhD physicists and then many more engineers, in fact, from over 100 different countries, speaking dozens of different languages, many different religions, all working together for a single purpose, which is what science can do. It can unify people from all cultures. It's what Google does here. Look at all the people from different cultures working for a common purpose. That's what science does. That's humanity at its best. And the machines are unbelievably interesting, complicated. This is one of the smaller detectors, well, one of the larger detectors, sorry. It's not the machine, it's just a detector in the machine. The smaller detector I have here is this called the compact muon solenoid, which is not so compact. It has this same amount of iron as the Eiffel Tower, for example. It's hard to see it. I have a better picture of it because I'm there. But it's really, when you go there, and if you do go to, and when the machine's down, you can every now and then go down. And it's just amazing to see the scale of everything compared to the scale we exist at. But the machine, you can't have almost enough hyperbole. I have a whole chapter in the book about it. For example, every second at the Large Hadron Collider, enough data is generated to fill more than 1,000 1-terabyte hard drives, okay, which is relevant to all of you. It's every second we have to process that much information, 1,000 terabytes of information in that experiment. And that means, as you can imagine, that you have to filter that information, and it's incredibly complicated, but interesting from a computer science point of view. But more than just that, for example, the tunnel that it's in has to be evacuated. That 26-kilometer long tunnel has to be evacuated so its vacuum is sparser than the vacuum outside the International Space Station. Every aspect of the machine is remarkable. And the fact that we're willing to do this to just address this question of why we're here seems to me to be the bravery of the people who devoted their lives to building this, and the people who devoted their lives to coming up with the theory is one thing. But the part of my book maybe the part of the title that's the best is the so far part. The greatest story ever told so far. Because the story gets better. Unlike that other story called The Greatest Story Ever Told, which was written down by Iron Age peasants who didn't know the Earth orbited the sun, is still the same, just as boring and untrue. This one changes. And it doesn't change just because we like it. It changes because every time we open a new window on the universe, we're surprised. And we're forced out of our comfort zone. And so I think of this, I happen to like Impressionist art, and I like art in general. But what I really like about Impressionist art is that it's beautiful from a distance. But when you get close up, it's really crappy. Okay? And that's science. Because great, we've developed this incredible model called the Standard Model that explains every experiment we can ever been able to perform in particle physics. But then the minute you make that discovery, there are always new questions. Why did this Higgs field form in the early universe? Why did it freeze in place? Why did it freeze the way it did so that resulting in our existence? All of these new questions. And the point is, this story will get better. Because the next generation of people, as long as we continue to ask questions and have the courage to be able to look out and try and find the answers, the story's going to get better. And the story will get better and more interesting and produce a universe that may seem more strange. And that story that we've developed and that we've now validated, as I say, is a story which is terrifying at the same time as it's awesome. And the consequences are ones we may or may not like. One of the first consequences, as I said, is that our existence is a cosmic accident in a real sense. just the same as on that windowsill. I mean, those people who live there, okay, that direction is very special, and it means a lot to that civilization. Just as all of the facets of our universe that look like the universe is designed for us, that therefore make it seem special, are accidents. The underlying universe is not only not designed for us, but as I said, antithetical to our existence. Because if the W and Z particles and all the particles in nature were massless, as they are at a fundamental level, if it weren't for this field frozen in the universe, then we wouldn't exist, because no bound objects could exist. There wouldn't be any people, any stars, any galaxies, anything that we could see. And these physicists on this window, on this crystal, might eventually discover that, you know what, this is just an accident of our existence, that crystals in different directions could form, and there's nothing special about that direction. And maybe they'll discover that at like 4 in the morning one day. But then at 6 in the morning, the sun will rise. In Seattle, you may know, there's this thing called sun. And it rise and it melt all these crystals. Okay, then their symmetry would be restored. There'd be no preferred direction. But the unfortunate thing is these people wouldn't exist anymore. And the interesting thing, and maybe terrifying thing, is that if you actually look at the Higgs field and look at the value it has, then it's just teetering on the edge of melting. Okay, the Higgs particle happens to have a mass that's very close to the mass where, if you look at the model, the field could be unstable and melt. And if that were to happen in our universe, then of course everything we see disappears. Okay? Now don't be worried. There's still time to buy books and stuff. But more than that, if you actually do the calculations, it's probably stable. But even if it's unstable, if you work out the time frame over which it might decay, it's not 1,000,000 years, not 1,000,000,000 years, not 1,000,000,000,000 years, not even 1,000,000,000,000,000 years. So this is a long process if it's going to end. But if it does, the universe will revert to this symmetric, beautiful form, but there'll be no life. So even this beautiful universe that looks like it's designed for us will disappear, and there'll certainly be no life like we see. And that, I want to just end with some notes about how this picture relates to the sort of history of science in a real way, because we're evolutionarily evolved to look for design. We always look for designs. Our eyes pick it up very well, and many of you are talented at looking for design, which is probably why you're here. Okay, but that design may not really be there, and we have to second guess ourselves. One of the things that Feynman really said, which is quite important, is the easiest person to fool is yourself, because you like something or you want it to be that case. And we all want design. You can think of human things that are developed like Christmas ornaments. They're clearly designed, but of course those aren't Christmas ornaments. Those are snowflakes. You just give me a polar molecule and laws of chemistry and physics, and I'll produce these beautiful things without any design. But you might say, well, what about human structures like the Google Plex or this building, or my favorite is Buckminster Fuller domes, because when I was growing up, every hippie had one and lived in them and did neat things in them. But they're evidence of a very interesting intellect, Buckminster Fuller, who was a really interesting guy, crazy but interesting. Well, just take soot. If you take soot, you'll find out in the soot are molecules called carbon-60, we now call Buckminster fullerene, which are beautiful geodesic domes. And there's nothing less designed than soot. So we have to be careful when we look for design in nature. The first real example of this was from one, of course, of the greatest scientists of all time, Charles Darwin. And if you haven't read the Origin of the Species, the last paragraph of it is really beautiful, one of the most beautiful lines in any science book everywhere. There is grandeur in this view of life with its several powers, having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms most beautiful and most wonderful have been and are being evolved. Now, this was a beautiful discussion of how the complexity and diversity of life on Earth, which appears to be designed, could arise naturally from simple beginnings by natural selection and evolution. And that design, like the fact that bees could find flowers, was not design. It was that if they couldn't see the colors of flowers, they wouldn't reproduce. And it could be understood from much more simple principles, and you could get incredible complexity from simplicity. This same paragraph could be used to describe the universe that we physicists are talking about. From so simple beginnings where the forces of nature may have been unified in a simple way, we as the universe evolved, produced structures like all the stars and galaxies and people and all the structures we see today by a simple process. And that universe is no more designed for us than life is. That we're carrying on that Darwinian process, which for many people is disturbing because they want the universe to be designed for them. It's comforting. Okay, but the universe doesn't give a damn what we want. And we have to learn that, the universe is made terrifying, but it's also incredibly awesome. And that a universe that isn't designed for us can actually be more interesting. It can be one in which our lives are more precious because the only purpose we have is the purpose we make. But, scientists, as I said, individual scientists are products of their time. So in a letter to Joseph Hooker, he said, "It's mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter." And in 1863, it was rubbish to think of the origin of matter. But now I get paid to do it, okay, because the story has gotten better. The story has gotten better because we continue to push the boundaries in our thinking, but equally important, in our looking out. We continue to be willing to build experiments and look out and be willing to change our perspective, even if it takes us in a direction we don't want to go. And I want to end by, in some sense, by saying I'm worried about this future at the present. In the current budget, for example, proposed by the President, the entire field I talked about, particle physics, the support for that is being reduced by 20%, $900 million. But more importantly, the agency that supports it, which is the Department of Energy, which most people don't realize is the chief funder of all physical science in our country, not just energy research, but all physical science in our country, is being cut by 20%. At the same time, the National Endowment for the Humanities is being cut completely, the National Endowment for the Arts cut completely, the Corporation for Public Broadcasting cut completely, the Institute of Museums and Libraries, which supports museums and libraries around the country, cut completely. You add all that up and you get $1.82 billion savings in our budget. Okay? In the same budget, proposed a $2 billion line item, which is the first installment of a wall with Mexico. Okay? So you got this wall that's going to protect us from hordes that are unknown, at the same time killing all of the support for culture and largely the support for science. And the way to picture that was actually, to me, expressed best by Robert Wilson, who was the first director of the Fermi National Accelerator Laboratory, the first big, no, not the first big, but the biggest accelerator in the world until the Large Hadron Collider was built. And in the 1960s, he was called before Congress and asked the question, will it aid in the defense of the nation? And here was his response. No, sir, I don't believe so. It only has to do with the respect with which we regard one another, the dignity of men, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in our country and are patriotic about. It has nothing to do directly with defending our country, except to make it worth defending. And that is a beautiful statement and is particularly poignant today, because we risk getting rid of everything that makes this country worth defending in an effort to apparently defend it. What makes America great, if anything does, is the contributions it will make and the people in it will make to the legacy, the future of our children, the perspectives of the world, our understanding, the new ideas we develop. That's why people, as you can see from here, that's why people come here from around the world, because there's some benefit, because the contributions we make for the future. If we get rid of all that infrastructure just to defend ourselves, the greatest story ever told will not continue being great, at least not here. And so I want to end with two quotes. One from the beginning of my book, which is a famous quote from Virgil. These are the tears of things, and the stuff of our mortality cuts us to the heart. It's from the beginning of the Aeneid. I remember learning that in Latin because I grew up in Canada and I was educated. But the next line, which is not so well known, but I point out at the end of the book, is release your fear. And that's the point. Only if we release our fear of the unknown, of others, of a universe that may or may not be the universe we like, only if we're willing to go into the unknown, will this greatest story continue to get better. And we may live in a universe that apparently has no purpose, apparently isn't designed for us, and apparently may be miserable in the future. But that's okay, because we are fortunate, more fortunate, to have evolved this consciousness that allows us to ask these questions for the short time and we're here, and so we should enjoy our brief moment in the sun. Thank you. Thank you.
So you made an analogy with the arts, and I think the obvious rebuttal there is that it's easy for people, anybody, to see the value in the arts. So to be, it's sort of directly titillating the senses. You don't have to be, you don't have to gone through a music school to appreciate a Bach. Or anything
You don't
like
have to be a scientist to look at the Hubble Space Telescope picture and see it's amazing. I mean, the point is that, you know what? If you do go to music school, you'll appreciate Bach a lot more. But you can appreciate Bach just by listening to it. But the wonders of the universe are easily appreciated by everyone, especially children. We beat it out of them.
Yeah, but
Okay.
like the Higgs particle, for instance,
Oh,
like
yeah,
that's
great,
a lot
but,
of explaining to get to that
Well,
point.
yeah, that's why I wrote a book.
Yeah.
But the point is, not everyone has to understand the Higgs particle, but it's there for those who want to get there, just like it's there for those who want to pick up a guitar and learn how to play it. But you don't have to understand the Higgs particle. What really need is anyone can understand the basic world around them if we provide them the opportunity, and more interestingly, and this is really important, if we teach science as it's supposed to be taught, which is not a bunch of facts. That's why we live in this world of alternative facts, because people in school are taught that almost all subjects are just a bunch of facts. Science is a process for discovering facts. And that's the process that anyone can learn, and we damn well better start teaching it. Because of Google, in particular, when I was growing up, that was the place to get information. But because of Google, I can get more information from this, but I can get also more misinformation. And the only way I can tell the difference is science, is skeptical inquiry, reliance on empirical evidence, testing my ideas, checking many sources. And so that's the thing that really is the greatest legacy of science, is that process. And that's the thing we need most, not just for the enjoyment of looking out at a Hubble Space Telescope picture and getting a kick out of it. I mean, everyone has had aha experiences. When I used to work at science museums when I was young, they're like orgasmic. We called them aha experience. When you suddenly see something in a new way. And it happens to everyone, and there's lots of science that we can do. But more importantly, those tools are necessary if we want to have an informed electorate who can actually distinguish policies that are related to empirical reality from policies that aren't. So there's actually an imperative as well as a joy. But I agree with you that at least the perception among the public is that you can enjoy music, art, literature with a much lower impedance barrier, as we call it in physics, much lower wall. It seems to take a little bit more. But I do think that's a product of our school systems.
Yeah, it's definitely worth it trying to.
Yeah, but I mean, I think if we teach kids not answers but questions, how to ask questions, we're all wired to want to discover the answers. And it's okay to not, I mean, the information is irrelevant in the school. Most of what you learn in high school is, sure, reading, writing, arithmetic, but beyond that, most of what you learn as an adult is going to be way beyond what you learn in school. Most of the physics I do as a scientist, I learned after my PhD. And so those tools are important, but the joy is there for everyone at different levels. And I think what we don't do well enough is tell people, it's just amazing how you can enjoy music without being a musician and you don't have to, but the common sense view is you cannot enjoy science unless you're a technical person. And we have to get over that, in my opinion.
I had a small question about your discussion of Berkeley earlier.
Uh-huh.
I was wondering what you think about scientists kind of believing in the theories they're working on without proof to drive it forward.
So they have to. Science isn't based on faith, but if you're going to spend 20 years of your life working on something, you've got to have I wouldn't call it a belief, but you'd have to say to yourself that there's something tells you it's strongly likely to be true. And you can be completely wrong. But the great thing that differentiates that from religion, let's say, is that if you're a scientist, in the end, if it's shown to be wrong, you throw it out like yesterday's newspaper, even if you spent 20 years of your life on it. That's the difference. But certainly you cannot work, the builders of the Large Hadron Collider or the developers of the Standard Model couldn't have done what they've done, or even the string theorists now. The people, my colleagues who do, I have students of mine who are well-known string theorists, so I just wouldn't want my daughter to marry one. But they have a good reason for doing what they're doing, and the hope is that somehow the theory will make contact with reality. But if it won't, you can be darn sure, and it's already happening in some sense. You saw when the Higgs was discovered that lots of string theorists went and jumped ship because suddenly there was new particle physics to look at. So yeah, we all have to. have that kind of faith, but the difference is that the faith in science is eminently shakable. The wonderful thing is that it is not ironclad. And that's supposed to be the great virtue of faith, is that you don't give it up. But in science, the great virtue of faith is that it has no utility beyond its utility. Okay? Okay? Good. Okay, I guess I'll thank you.